right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. We're in the middle of some examples last time, so let's actually just jump into it. There we go. Should be able to see my screen. Just a very, very quick recap before we jump back into it, because now we are going to be doing some examples to illustrate some of the definitions I was talking about, at least in regards to sets. We're not going to really talk about tuples today, but we have some examples to do with sets, including one example I want to get through to do with Venn diagram word problem, and I'll leave you guys with some examples to try out for next class. So for the past couple classes, we've been talking about sets. Set is an unordered collection of objects in which we don't care about repeats. Many things can be modeled by sets, and this is how you actually write them down. You can name them with uppercase letters usually, and you can write them in something called the roster method. You can list them in those squiggly brackets. If you want to say something is in a set, you can use those symbols. Not in a set, you can use that symbol. Sets are called equal if they have precisely the same elements. So a set is defined by its elements. Every now and then we care about the order, and we also want to count repeats. Whenever we do this, we can't use sets. We use what we call tuples, which are kind of like ordered sets that account for repeats. So the order in which we list in this kind of object matters, as well as if guys show up several times, it matters that they show up several times. And there are a lot of situations in which we'd want to do that. So we talked about n sets and n tuples. That's just a name talking about the number of them. Talk about the size of a set, called the cardinality. Basically, it's the number of elements in them. Makes a lot of sense when the set is finite. This means the number of elements in it can be described as 0 or a positive whole number. So I can say there are 0 things in this, or there are 3 things in this, or 5 things, or 7 things, or 11 things, or a million things, right? So once you can actually say that, you can state an integer number of things. We call a set a finite set. If you can't do that, you say it's an infinite set, right? You can't actually state it, how many things are in there with some positive non-negative integer. So the size is just how many things are in there, right? So that's that. It's called a cardinality. The empty set is a set with cardinality 0. It's a set that has 0 elements in it, no elements. We also spoke about subsets. This can be thought of as a sub-collection. So you can have a set, and then from that set, you create other sets. These other sets that you create are called subsets of the original set. And so the technical definition is A is a subset of B if everything in A is also in B. And of course, if you created A from B, then yeah, anything that shows up in A would also have been in B, because you took the things from B to put it into A, right? So that's what it is. Subsets can be potentially equal to the entire set that they were created from. They can also be empty. You can take an empty subset. And we have some symbols on that. So the fact that I just mentioned is the empty set is a subset of every set. Every set is a subset of itself. And in fact, 2 sets are equal if they're subsets of each other. If everything that's in A is in B and everything that's in B is in A, it means that they have precisely the same members. Therefore, they are equal. We looked at the power set, which is a set of all possible subsets. We saw that if a set has n elements, the size of the power set has 2 to the n elements. We used an argument called the multiplication rule to figure that out, something that we will be talking about in more detail next week. If not at the end of Tuesday's class, towards the beginning of Wednesday's class. So we will move on from there. So those are just some of the basic definitions. Some more basic definitions is equivalency as opposed to equal. 2 sets are equivalent if they have the same number of elements. The elements themselves might not be the same. So here, A is 1, 2, 3. The set B has A, B, C in it. A is not equal to B because they don't have the same elements. However, they are equivalent, or numerically equivalent, we call them. Common number sets are the natural numbers. Remember that some people start this from 1, but you have to be careful of what the source that you're reading. The source material will tell you. For us in this class, I'm going to assume the natural number starts counting at 0, 0, 1, 2, blah, blah, blah. We also have the integers, positive and negative whole numbers, and 0. We have the rational numbers, set of all possible fractions. We have the real numbers, every number on the number line. And we have the complex numbers, all numbers in the 2D plane that can be represented where the vertical, the y coordinate is attached to the square root of -1. All of these sets are infinite, but it turns out that some infinities are bigger than others. The first three, the natural numbers, the integers, the rationals, they all have the same number of elements, quote unquote, even though they have an infinite number of elements. This number is called Aleph Naught, by the way, a Hebrew letter. And the real numbers has more elements than all of these sets, even though it's also infinity. The complex numbers has the same amount of numbers as the real numbers. And so the infinity of the real numbers is larger than the infinity of, say, the integers. And it's larger by like a lot, as I mentioned. Like the difference between the ocean and a drop of water is significantly bigger than the difference between the real numbers and the integers. So yeah, it's bigger than a lot, by a lot, like remarkably so. There's also the concept of a universal set. Our sets are not spontaneously generated. They don't just appear out of nothing. We always assume that there's a universe of things from which we can create sets that's in the background. This is called the universal set, right? So every set I create is considered a subset of some background set, some universe set, which is not unique. We state the universal set for the current problem that we're going to be in. And when we get to probability, our universal set is usually going to be called something called the sample space. We'll get to that later on. The complement of a set is everything that is not in that set, but is in the universe. So all things in existence that are not in the set A is said to be in A complement. And we have the notation for that. We did a little example there. We also talked about Venn diagrams. This is a way to illustrate visualize sets. Consists of a box with a bunch of circles. The circles represent sets. The box represents the universe. We usually label them in terms of cardinality, and this can help us solve problems, which we'll see later today. Then there are set operations. How can we combine sets and operate on them? Kind of like how, we can combine numbers and add and subtract, but it's of course going to be very different with sets because they're not numbers, not technically. Well, technically numbers are sets, so never mind. The union is an operation in which we combine two sets. We take all the sets in either A or B or both, combine them into one big set. Of course, because we combine it into a set, you would ignore repeats, but it's just a conglomeration of all the elements in the set. And that's read A union B. We have the intersection, which is the set of all elements that are in common to both A and B. This is called A intersect B. Notice that we can talk about A intersect B being empty. This means that A and B are disjoint. We also spoke about the set minus, which is not quite like the subtraction that you're used to, but it's a kind of subtraction that deal with sets. Basically, A minus B means you take A and you subtract from it everything that's also in B. So you start with the set A, you throw away everything that's also in B. You have now obtained the set A minus B. We can visualize the above with pictures. The union means what's in either set. The intersection means what's in both at the same time. A minus B is everything that's in A but not in B. B minus A, everything that's in B but not in A. A is just, of course, a set which A is shaded. A complement is everything in the universe that is not in A. Tip with Venn diagrams, remember, you always draw them to have the maximum amount of overlaps as possible. Unless you know for sure there's a very good reason to not draw something overlapping. It's probably better that you draw it overlapping than not. If you draw an overlap and there's actually nothing in the overlap, you can always just put a 0 in the overlap. It's really not a big deal. But if something should overlap when it doesn't, then you're in trouble. You won't be able to actually fill in a number anywhere where you should be able to fill in a number. And then I left you guys with these examples here, which we're going to do all these examples as well as one additional example. And that's going to be today's class. So we're going to move over here. We're going to do these examples which I left for you last time. Hopefully you actually looked at those and tried them. But there are also, in addition to that, some word problem examples that I want to do with Venn diagrams. We'll only get through one of them, but I'll leave the other three for you to try. You'll definitely be tested on it, so I definitely want you to try it on your own. Whew. Okay, that being said, let's actually get to the problems. Make sure that we understand our definitions, how they work, and create some space here. I'll probably actually want to mention something about Venn diagrams before actually starting the examples. All right, let's jump into it. A intersects B complement, and let's compare that to A complement union B complement. The question asks us to compare these via Venn diagrams. So let's actually do that. Draw it with overlaps, because I really don't know what the answer is going to look like at this point. So I draw with overlaps. Now, we saw A intersect B in the last time. That is this region here. That's A intersect B. So what is A intersect B complement? Someone tell me quickly what that would look like.
Would that be A as well, or no? Because I understand that a complement is like whatever that's like kind of the opposite of what B would be, or is it on the outside?
Right, but the outside of what?
A or B.
Yeah, so what I just shaded was A intersect B, right? That's the red that I just shaded.
Yeah.
So what would its complement look like?
So does the complement on the outside of the parentheses, is that just for the B or is that the A as well?
Well, it has parentheses around it has parentheses here. So it applies to everything inside the parentheses.
Okay, so the complement would be outside of the Venn diagram?
What do you mean outside the Venn diagram?
Like in the box, but outside the circles?
No, not quite.
Okay.
So again, remember what complement means. It's everything in the universe that is not in the current set, right? So my current set is the intersection, right? That's A intersects B is the set I'm looking at, which I shaded in red, right?
Oh, so is it just A and B now?
So what is the complement of what I shaded in red?
A and B.
No. So so I have to make sure that we understand the definitions. Where did I do complement? I forgot. Yeah, the complement is the set of all elements in the universe that are not in the set, not in A, right? Now the universe is the entire box. Everything that's in the box is the universe, right? So here's a set. I have the set A intersect B, which is shaded in red. The complement is everything in the universe except that. So what would that consist of?
So the box is everything in the universe. So
yes, the universe is the box.
So it's everything but what's in the universe. So outside of the box. But I don't know how you shade that.
I mean, I'm glad you're thinking outside the box, but that's not no, there's nothing outside the box, right? Outside the box doesn't exist. The box is everything.
Okay.
Right? So if the red region is the intersection, and I want the complement of that, what I'm saying is I want everything in the box that is not that, right? Which means it's going to include the part in A that's not in the red part, the part in B that's not in the red part, and everything in the box that's outside of either circle. It's literally everything except that, right?
Okay, got it.
So that would look like this. So not only is it A and B, it's also everything outside A and B as well, right? The only thing that's not shaded is the actual intersection, right? So, which is good. So this is why I'm doing these exercises, because I really want you to understand the concepts, the definitions that I'm giving you, what they mean, right? So when I say complement, you find the set that I'm talking about, and then you literally take everything else, right? And everything is the box. There's nothing outside the box. The box is the entire universe. So I know the intersection was what A and B have in common. I literally want everything other than what A and B has in common, right? That's the point of the intersection. That's the point of the complement. Now let's look at A complement and B complement and take the union. So let's say I wanted to shade A complement. What does A complement look like if I wanted to shade this in blue?
Is that everything but A?
Everything but A. Everything, literally everything outside of the A circle. Now, what if I want to shade B complement? It's literally everything but B. Everything outside the B circle. Now remember, the union says we want anything that is in either set or in both sets. So the union is the guy that says union wants all shaded parts. Right? If there's shading, it's a part of our union. So the union is equivalently becomes, so if I look at A complement union B complement, and I'm going to shade that green now. Any part that was shaded at all is what I want in my union, which now you'll notice is everything except what is in common to A and B. So that being said, what would you conjecture for these two sets? A intersect B complement and A complement union B complement. What would you say how do they relate to each other? What's the relationship that you would guess from these pictures?
They both have everything shaded except for the overlapping the.
Yeah. So how would you describe that?
Correct. I do not know.
What you just said, in other words, is they all have the same elements. The things that are in both sets is everything except the thing that they have in common. So they have the same elements. So what are you saying when you say that?
They both have the same. I'm trying to like think of the correct. They both have the same things in common. I don't know how to say this.
You probably don't want to say the things in common, but they both have the same elements, right? The blue region and the green region are the same, right? Like if I change the green color to blue, it would look like exactly the same picture, right? They all have the same elements. What does it mean for two sets to have the same elements? What can I say about sets that have the same elements? What is the word we use to describe that? Mathematically speaking, it's a very intuitive word. So it's not a weird word like, oh, I've never heard that word before.
They equal each other?
Equal. They're equal. That's the word we would use. So conjecture would be, these guys are equal. If I take the complement of an intersection, it is the same as taking the union of the individual complements. We would conjecture that they're equal. Conjecture is just a fancy mathematical word for a guess. It's an educated guess. Right? So the word conjecture in mathematics means kind of like the same thing as hypothesis in science, right? I have a guess as to what is going on here. I mentioned last time that pictures are not proofs. You can't actually use a picture to prove anything, but you can kind of hint at a guess. Like the educated guess based on the picture would be that they are equal. It turns out that they're in fact equal, but the picture is not the proof of that. So yeah, so that's what we can say about that. D, we have the other one, the complement of the union. So if I take A union B complement, and then I take A complement intersect B complement, that was the other set I was looking at. So being able to know what region you are looking at is very important, especially for word problems later when we're going to be doing Venn diagrams. You're going to need to know what region would be shaded, where should I fill in this number, things of that sort. So you really want to know where these guys are. So A union B, we know what that is. A union B is everything that is in either A or B. So what is the complement of that? Literally everything else, right? So that would be everything outside either circle. Okay, so that part is not so bad. Now let's go where we take the intersection of the complements, of the individual complements. Let's say I'm going to shade A complement like that in blue. So that is going to be that, everything outside the A circle. Let's say I did B complement like this in red. So that's everything outside the B circle.
I had a question.
Yeah.
Why is the their intersect not shaded in as well with everything outside of?
Because the intersection is in the union.
So it still counts as.
So it still counts. If you go back to the definition, here's union. It's what's in A or B or both.
Okay, so even when you're doing.
So this is in the intersection as well. So the union would include the intersection, but also things that are in either set.
Okay, thank you.
So the union is literally everything in A or everything in B or everything in both. So it's just going to be the entire circles. So now the complement of that is literally everything outside of that in the box, right? A complement is everything outside of A. I shaded that in blue. B complement is everything outside of B. Shaded that in red. Now, what is the intersection? It's what they have in common, right? So what does that mean in a picture? Intersection, what does that care about? The union cared about any once it's shaded, I care, I want it, right? The intersection doesn't care about that. The intersection says, I want what's in common. So intersection, how did I phrase it? Wants. The intersection wants what it wants. Wants regions where all shadings overlap. You need everyone to be in common. meaning it's not good enough that it's like this part isn't good enough that's shaded red but not blue. This part is also not good enough because it's shaded blue but not red. It means that they're not in common, right? The blue part and the red part, they're not in something that they have in common. I want the part with both shadings, right? So that means here, what I want is the part that's shaded both with blue and with red at the same time. So that leads me to, let's say A complement intersect B complement. So I want the part with both shadings. So if I were to shade the parts that have both shadings, all the parts that have blue and red at the same time, I need both for the intersection. That would be that. And what can we say about these two based on the picture? Well, notice that if I shaded them both in the same color, they would look exactly like the same picture. Meaning these sets have the same elements, meaning they're equal. So if I take the union. If I take a complement of union, it's the same as taking the intersection of the individual complements. It turns out both these conjectures are actually true. They lead to a theorem. Does anyone, I mean, after I did this, does this look familiar to anyone? Does anyone know what this is called? I don't know if you guys did stuff with sets in high school. These guys are called De Morgan's laws. Very, very famous rules, very useful rules. You can't study set theory and not have heard about this. For any sets A and B, we have one, the complement of the union is the intersection of the complements, and two, the complement of the intersection is the union of the complements. These guys are called De Morgan's laws, very important. And we illustrated them with Venn diagrams. So the pictures aren't proofs, but they can kind of suggest what the truth might be, give you a nice conjecture or hypothesis to work with, and then you go through and see if it actually works out to be true. To prove these, it's a little bit more complicated. But hopefully by me doing that, you now have a better appreciation of what a complement actually is, what a union actually is, what an intersection actually is. Now let's go with some specific examples where I give you the sets. The U represents the universe, remember, and I defined this for you before as 0, 1, 2, 3, going on forever. So now I want you to find all of these guys. So need some space in here. should have put those up more. Okay, now let's go back here. All right, A intersect B. So A is a set 1, 2, 3, B is a set 3, 4. What is the intersection?
Three.
It's the set containing 3. Yes, remember the intersection is also a set, so you have to write those set symbols. If you only write down the number 3, it would be incorrect. Very important that you know that. 3 is the element, the intersection is a set. So you have to write the squiggly brackets. Braces, important. What about A intersects C? A is 1, 2, 3. C is 4, the set containing 4 and 5. What is the intersection? Intersection? Anyone?
There isn't an intersection.
There isn't. How do you say that then? How do you write that down? There are no elements in common, right? So what set are we looking at then?
Would you just write no real numbers? Or is
No.
that
You write the answer is always going to be a set, right? So it has to be the empty set. And it doesn't have to be numbers. So remember, we spoke about, maybe that was in the previous lecture. Yeah, we spoke about the empty set. That's a set with no elements. So if you want to say no elements, you say the set with no elements, you say the empty set. Then you have to remember that when I defined intersection, the intersection itself is a set. So it's not like a phrase like no real numbers or something like that. The intersection is a set itself. It has to be some set. Now, if your set just has nothing in it, it means the set is empty. So it's just the empty set, right? So these guys are the empty set would be the answer. Or you can write like a squiggly, but don't put anything in it. But it's more common to write that, the circle with a slash through it these days. So this is definitely going to be a set. These are all sets. A intersects E. E is a set of positive integers. 2, 4, 6, 8, blah, blah, blah. A is a set 1, 2, 3. A has what in common with E? Well, it has only one thing in common with E, namely 2. So this is a set containing 2. I want A intersects with O. So A is a set 1, 2, 3. O is the set of all positive odd numbers. So it has 1, 3, 5, 7, all the way. The intersection is what they have in common. Notice that what they don't have in common is the number 2, but number 1 and 3, there's overlap there. So that is 1 and 3. E intersect O. So we want the things, the set of all things that are in both E and in O at the same time. You'll notice that O has all the odd numbers. E has all the even numbers. There is no overlap here. You can't have a number that's both even or odd, which means there are no elements that are in both E and O at the same time. Hence, empty set is the answer. A minus B. So this is also a set. What it means is you take the set A and then you throw away anything that is also in B. So the set A is 1, 2, 3. The number 3 is also in B. Therefore, you would throw away the 3 and you'd be left with the 1 and the 2. So that's what a set minus means. So here, start with A. Then, see this 3 here? You get rid of it. Throw away, then throw away anything also in B. So I would take the set A and I would throw away the 3. And that is A minus B, quote unquote. C minus A. What is that? You go to the set C and you are going to remove from that set anything that is also in the set A. But there's nothing in C that's also in A, which means the subtraction doesn't do anything. It's still just a 4 and a 5. C minus A is still C, right? So there's a difference between subtraction in sets and subtraction of numbers. So you can have something and you subtract something that's not nothing, right? It's not the empty set, but it doesn't make a difference because of how set minus works. Very important that you know the definitions here. N minus E. So I look at everything that's in N, and I'm going to throw away everything that is also in E. The things that are in E are the 2, 4, 6, 8, blah, 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 which means N minus E is going to be the 0, the 1, the 3, the 5, the 7, the that. So this is going to be like 0, 1, 3, 5, 7, dot, dot, dot. It's going to be 0 plus all the, in addition to all the odd numbers. So this is, you can think of this as O union the set containing 0. That's one way you can think about it. That would be the answer. If I were to take E minus N, what is going to be that? What is that going to be? E is the set of all even integers, 2, 4, 6, 8, blah, blah, blah. E minus N means I start with E, and then I throw away everything that is also in N. But guess what? 2, 4, 6, 8, all of that is also in N. So if I start with E and I throw away everything that's also in N, I'm literally throwing away everything. So that's the empty set. And yeah, so hopefully that's clear. So the point of these examples is to get you really used to what the definitions mean, and of course, getting you to pay attention to the definitions, knowing when it's a set versus not. Because if you did this on a test and you only wrote 2, but you didn't write the squiggly brackets, it's wrong, right? And you need to know that. You need the squiggly brackets because the definition is this is a set. The intersection of 2 sets is also a set, meaning it needs the squiggly brackets, right? The intersection of a set is never going to be an element. It's going to be another set, right? And so on and so forth. All right, and we have these guys. Let's make a little space here. Okay, so now our universe is the set 1, 2, 3, but 4, 5, going all the way up to 10. The first 10 positive whole numbers. This is the universe. What that means is for the sake of this problem that we're currently in, This is all things in existence. U is everything that exists. There's no number 11, right? So it doesn't exist now, right? We only have numbers 1 through 10. So you don't have a -5, you don't have a 7, you don't have a 17, you don't have a 100. Like, it doesn't exist, right? There's no 11 and after, which kind of reminds me of this joke I heard once about the 9/11 deniers. You know, the 9 people who denies that 11 is, no, never mind. Okay, so we have only these numbers in the universe, right? There's nothing else. Okay, then I take the set A, which is 1, 3, 5, 7, 9. These are all the odd numbers of all the things in the universe. And B is 2, 4, 6, 8, 10. These are all the even things that are in the universe, right? There's nothing outside of these numbers. Okay, so now, what is A intersect B? A intersect B is the set of all the things that these two sets have in common, but they actually don't have anything in common. So that's the empty set. What about A union B? So this is just a combination of all the things that are in either set. So it has to be in A or in B or in both, which means it has 1, 2, 3, 4, all the way up to 10. It's actually the entire universe. What about A minus B? A minus B means you start with A, and then you throw away anything that is also in B. However, there's nothing in A that is also in B, which means you don't throw away anything. You're still left with the 1, 3, 5, 7, 9. You're still left with A. Someone's trying to get in here. What about A complement? Now remember the definition of complement. The definition of complement is everything in the universe that is not in this set. The universe is all numbers from 1 to 10. A is all the odd numbers from 1 to 10, which means A complement must be all the even numbers from between 1 and 10. So this is going to be 2, 4, 6, 8, 10. In fact, that is the set B. What is A intersect B complement? Now, there are a couple ways you can look at this one. And in fact, I'll probably mention both ways. So one, you can think of this as it's the set of all things not in the intersection. Okay, so I just want to find all the things that is in the intersection and then take everything else. What are the things that are in the intersection? Well, we already found the intersection up here in part A. The intersection had no things in it, which means everything else is literally everything else. Everything else is going to be all the numbers from 1 to 10. This is the universe. There was another way to see this, just to illustrate something that I mentioned earlier, is recall De Morgan's laws, right? My A intersect B complement is the same as A complement union B complement. What is A complement? Well, we actually found that already. That's actually B. Similarly, B complement is actually A, right? Everything that's not in B are just all the things that are in A. And what is B union A? Well, we actually saw that that was the universe in part B. It's all the numbers. This is 2, 4s all the way up to 10, and this is 1, 3, all the way up to 9. It's actually everyone. So it's 1, 2, all the way up to 10, which is the universe. Which we had before. But there are a couple ways to see this. There's a more intuitive conceptual way, and then there's like using De Morgan's laws and actually calculating it. Similarly, A union B is everything. We saw that right here, which means we want the opposite of everything. What is there that is not in everything? Well, nothing, right? A union B complement is the universe complement. This is going to be the empty set. So there are two facts here that are true in general, not just with this example. And it is the following. Fact. The complement of the universal set is always the empty set. And the complement of the empty set is always the universe. This is something that's true now. We know that now. We can take that for granted, just like we can take De Morgan's laws for granted. Yeah. What is the opposite of everything? Well, nothing, right? So if I look at the opposite of the set of everything, it's going to be the set of nothing. What is the opposite of the set of nothing? Well, it would be the set of everything, right? Everything in the universe. Not everything generally, because that leads to mathematical contradictions, but everything in the universe we're currently considering, right? So we're already a little bit over time, but I'll just talk about this because I got to it in the other class. Venn diagrams. Want to be able to solve word problems with Venn diagrams? I'm just going to solve the first one and leave you guys with the others. There are some tips though, so I should just mention those. We want to be able to use Venn diagrams to solve word problems relating to the size of sets. The following method generally works. So how do you actually go about doing this? One, you would define your sets. That means give them a name, right? So let A be the set of this, B be the set of that, based on what the word problem is talking about. Two, we're going to draw a Venn diagram. With all the sets. Remember, draw with maximum overlaps. Unless told specifically that certain sets don't overlap. You'll never be wrong by drawing too many overlaps, but you can potentially be wrong by not drawing an overlap. So I would be careful with that. 3, you're going to fill in the cardinalities. Fill in the cardinalities of each region. Each region in a Venn diagram represents some set. Tip, fill out in this order. You can get in trouble if you fill out the wrong things first. 1, regions of max overlap, where everyone overlaps, if given that information. Generally, fill out regions with more overlap before regions with less. So like if I have a Venn diagram, there are 3 sets in it, I'm going to draw all of them overlapping. I would want to fill out the sections where all 3 overlap before I fill out the sections where only 2 at a time overlap, before the sections where only 1 overlaps, and so on, right? You kind of want to go for the most overlaps first, because otherwise you can actually get into trouble. The second time is regions where your regions designated as only. So sometimes a word problem would say, in this set, there's only this people, and then you can just fill in that number. Otherwise, if it just says, in this set, there are this many people, that might not be the number that you should be filling in, and you should be very aware of that. And we'll actually see that in the first example. Region outside all circles. Provided this info is given. You'll always have enough info in a problem to fill it out. So, but you look for what information you're given. You want to fill out these numbers first. The fourth thing is, it's actually just arithmetic. Use basic arithmetic to find the cardinalities of any remaining region. And that, at that point, you're pretty much almost done. After that, you just answer the question. The hard part is the steps 1 through 4. So let me quickly show you what that would look like here. Suppose you have 100 people in a school. 50 of these students remember all the math they've ever done. 40 of the students are in math 1108. Out of the math 1108 students, 20 of them remember all the math they've ever done. I want you to figure out how many students who don't remember all the math they've ever done are not 1108 students, and how many 1108 students don't remember all the math they've ever done. So that's the basic question. So the first step is to define your sets. So I can say let M be the set of math 1108 students. Let R equals set of students who remember. Of course, it's implied that U is the set of all students at the school. So that's us defining our sets. 2, we're going to do that Venn diagram. So Here's my school. I have two sets. I draw them overlapping. Math 1108 students, students who remember everything. 3, fill out Venn diagram. So I can do it that step. So I go and I read. And again, there's a certain order I want to fill things out, looking for the place with the most overlap. Notice here, of the Math 1108 students, 20 of them remember all the math they've ever done. That's an overlap between Math 1108 and the students who remember. Which is the most overlap? 20 would go here. First thing I fill in. Now let's find the other part. 40 of the students at the school are Math 1108, which means in the M circle, there are 40 people, which means over here, I should have 40 minus that 20 that I already accounted for. So over here, I also have 20, right? Now, if I had written the 40 in that circle in the beginning, I would be in trouble, right? Because then it would tell me that there are 60 math students. So you don't want to fill in the number just willy-nilly. You really have to think about it. And let's look at, we know that 50 students remember all the math they've ever done. So that means there are 50 students in the R circle, but I have to subtract the 20 students already accounted for in the intersection. So that means that leaves me with 30 students out here. So just to mention order in which we filled out is I first fill in the 20, I then filled in the other 20, I then filled in a 30. Then I know there should be 100 in total. So this would be 100 minus 20 minus 20 minus 30 equals, well, 30 out here. So then I fill in the last 30. So this leaves me with a diagram like this. 20, 20, 30, 30. Let me keep the colors here because that's going to be important for later. Okay, so that's how your Venn diagram will be filled out. And now I can answer the questions. And it will be remarkably easy to answer the questions. How many students who don't remember are not Math 1108 students? So I don't want them in the R circle. I also don't want them in the M circle. There are 30 people that fulfill such a criteria. Not in R circle. Also not in M circle. Right? How many students who don't remember, meaning they're not in the R circle, who are also not Math 1108 students, which means they're not in the M circle. So now I just pick the number that is not in either circle, which is the 30 over there. That's written in white. Second question, how many Math 1108 students don't remember? So basically, this is asking for those in the M circle, but not the R circle. So they're in Math 1108, but they're not in the remembering circle. So they have to be in the M, but not the R. So the answer there was the 20. And of course, in like a test, all these numbers would be different. I'll know that you know which number you're picking and for what reason, but that was just an illustration. So pretty much that's it. I'd like you to go through and do these guys where some of these you'll have like 3 circles, up to 3 circles, maybe even more. But yeah, that's how you would solve something with Venn diagram. In terms of cardinality. So someone can tell you how many people they have in which sections, and you can use that to kind of figure out how many people should be in other sections. But we're already way over time, so let's get out of here. Thank you for your time and attention and sticking around. Let you guys go. Have a good rest of your day. Have a good weekend. I will see you guys in the next one. Ciao.